Oh shit. Compute node. Uh, 309, right? So 5 o'clock on reset. Okay. Now I have to wait. Oh, just kidding. Okay, so yesterday, I tried doing this on Vista, or like setting up an environment on the Vista machine, but unfortunately, its architecture, which is ARC64, it's not complying with it, and so I have to work with LS6 or the Lone Star machine, but we don't have too much compute, so I have to be careful, and I don't know, I can't really run too much experiments. So I think the plan is I really have to focus on the actual code and making sure that there's no bugs first, maybe locally, and then if that works, and I like know for sure that like we're getting the right predictions, we're getting the same format of the predictions that we want, then only if and only then I will run on a compute node. But I don't know, it's kind of hard, and I will have to talk to my advisor, but maybe he can help with setting up an environment on a Vista, but we'll see. So failed yesterday, and I will ask my advisor for help. We'll see. Alright, and I'll just note this as work in progress. Alright, today I will set up a loss function. So initially I thought that, well, I sent an email and my advisor answered some questions I had, and I was kind of wrong about a lot of things, but maybe I can set up my whiteboard. Okay, let me see if I can set this up. Oh, I need to wipe out my table. Okay, let me pull it up. Okay. Is this live? Well, I know I'm live, but is this whiteboard live? Okay, let me just scribble. Oh, that's so sick. Okay, nice. Let me undo. Wait, can I erase though? Okay, good. Alright, where was I? Cool. So, I guess current status. So, current plan of, I don't know, what do we call this? Wow, this is really slow. What do I call this? Okay. Ribosome profiling. Model pipeline? Okay. Model pipeline. Oh, my hand. Okay. Pipeline. Nice. Alright, so from my understanding, and I still need to understand that, the biology context to its fullest, but from my understanding, there are going to be 3 predictions for each RiboSeq. Actually, now that I think about it, if any random, like, outside my friends that actually, like, watches this, I guess I could explain, like, my current understanding of the problem. But essentially, given any RiboSeq or transcript codon sequence or a sequence of multiple codons or nucleotides, right? What is a nucleotide? Well, I took biology in high school, and I know there's ACTG, right? So nucleotide can be represented. Well, let me search up the names. My Wi-Fi is really slow. There's adenine. Okay, cool. So, what do we have? We have adenine, guanine, thymine, cytosine, and uracil. Well, I do know that uracil actually, depending on the context, uracil will replace one of them. So it really depends on the context, but essentially, you're given 4 different nucleotides, right? And so, in my context, it's ACTG, so adenine, cytosine, thymine, and guanine, right? And so, we have, hold on. Adenine, right? AC, so cytosine. It's called that, right? Yes, it is called that. Cytosine. And then we have thymine. That's what the T is for. Okay. Thymine. And then G, which is, what is G? Guanine. Okay. Cool. Okay. All of this leads to our neat little ACTG, not acronym, but just, I don't even know what you call that. Well, anyways, our input data, right? So, our input data will be, hold on. Input data. So, given a sequence, right? So anyways, oh yeah, also a codon, right? One more thing. A codon is just a set of 3 different nucleotides. So, right, in this example, right, for example, ACT, right, from ACTG would be a codon. CTG would be a codon. TGA, let's say we extended it, we had ACTG multiple times, right? The list goes on, right? So these are examples. Okay, so we have this. Why I also wrote it in this order is that there's something called a codon frame, or frame. I will call it codon frame, actually. I think that's what it's called. But you can make predictions, and I'll talk more about it, like go in detail later. But essentially, like this model pipeline is making predictions, right? Predictions that calculate a number per nucleotide, which is the ribosome occupancy. And the benefit of that, when you calculate, or if you know the ribosome occupancy of an entire genome, then you can kind of, like from the unknown genome, right? Because the point of all of this is that we have like known data, or like we know exactly certain attributes of a specific genome, right? But the thing is, there are more nucleotide, and the length of it, right? The length of all of this in biology, there are more nucleotides out there than there are, I believe, atoms in the universe, if I recall. Now, correct me if I'm wrong, but I believe that is a saying, and that is true. But that might also be wrong and sound very, very stupid. Regardless, we have known data, but we want to create models that predict, or make predictions and analyze the transcripts or the sequences of unknown things that we encounter in biology. And that's why we make this. And so one of those predictions that you can make is the ribosome occupancy. And if you can do that, that can contribute to larger efforts and actually help scientists that work in that space to develop new diseases or other important things that could benefit humanity. So it's really cool stuff. But going back to the nucleotides, and so I said that our model's trying to predict a value which represents the occupancy per nucleotide. But sometimes the data can actually be very noisy from experience, and sometimes it's actually better to group the nucleotides together. Now, in the biology context, a group of 3 nucleotides would be a codon. And why I brought up frames earlier. So a specific frame, so like let's say you have, I'll erase this later, but like let's say you have ACTG, ACTG, right? So this is a specific nucleotide. It should appear anytime soon. Just give it a bit. Okay, there we go. Right? So this is a specific nucleotide. Now a set of these 3 things, so ACT is a codon. And the last part, right? So you can predict a number based on the codon, or you can predict it based on the nucleotide. And right now, I'm trying to have the pipeline predict values based on each nucleotide in their position. But later on, once everything's set up and that compiles and works, then they'll work on the codon portion. But sometimes, because of the noise, it's better to actually group the nucleotides together and make predictions based on the codon, so the noise doesn't actually affect the parameter updates in the model, right? Or the training of the model that much, right? There's less of an effect from noise, and we can better focus on the actual context, that the features that matter to us. Now, there's one more part to this, so you can't just actually pick the first 3 and then the next 3 and call that a codon. There are things called codon frames, right? So even though you're trying to minimize the noise, right, you still have to repeat it 2 more times and then repeat that prediction per codon 2 more times and then average the 3. And why is it 3 times? Because not only, so if we look at this example, not only is ACT a frame, CTG is a frame, and then TGA is a frame, right? And then if we go to GAC, well, that just goes back to, that's the same thing as just going to the next codon past ACT, right? So GAC would be the next thing, right? I don't know if that really made much sense to anyone that does watch this, but I mean, I don't get any viewers, so I don't really care. Anyways, that's important because if you go codon, like if you go to codon 1 and then you go to codon 2, you're essentially skipping out on information provided by codons like CTG and TGA, and that is not good. That could actually, you can't just remove context, you need the full thing, right? And so that's why when we do codon prediction, you might think, oh, it's faster if we instead, like training would be like 3 times faster because instead of making predictions per nucleotide, we predict it per every 3 nucleotides, right, at the same time. One iteration would be true, but yeah, it's actually not because you need to do it for CTG and TGA. So the training time is actually the same. And that was something that my advisor had to clarify for me last week. Not last week, 2 weeks ago. And it made a lot more sense in that regard. But anyways, that is a problem for another time, but that is essentially the context, right? So you're given a sequence, so ACTG, and then blah, blah, blah. But like, there's obviously like millions of them, right? Or billions, I'm not sure. Given that sequence, you need to predict the ribosome occupancy, right? Last thing, one visual that would probably help, what helped me, was that if you just like plot it on the graph, so like, let's say you have ACTG, blah, 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 ACTG. It takes a while for the whiteboard to update, but it should be good, right? Let's say you have a little graph, right? Numeric predictions for each codon or nucleotide, and then we can like go up to 1,000 here or something, right? It's some arbitrary value, and if we can plot those predictions on a graph, at least to help us visualize, it would look something like this. Hold on. Wait. Why is it not? Hold on. Okay. There we go. Why is it not working? What the? Okay. Hold on. Is my pen charged? Wow, it's just not working, is it? Hold on. Okay, but that works? That's weird. That's so dumb. Okay. Good. The pen works now. Okay, cool. Hold on, let me just uninstall this. Okay, so going back. When you make a numeric prediction across the sequence, right, it's some number, right? And if we just plot those numbers on the graph, right, with the sequence as our x-axis, that would genuinely look like this. I don't know. Something like this, right? So maybe in some regions or codons, right, they'll have high occupancy, but in some other regions, right, like here in the middle, right, I don't know what it would be. This is just an example. It would be a lot lower, right? And so we know what, so for specific parts of the genome, right, we know like these exact values. Like it's a fact because we've measured it, but there is a whole other world out there that we don't know anything about, that's like other sequences, right? So if we just take all of this data of our known data and we feed it, maybe, and just maybe, we can have a model to predict that. And so my lab actually did that, I think for the first time. Well, not for the first time, but I know UT had an article on the lab before I was a student, and their first model of it was ribbon, actually, that's what they called it. So my grad student, actually, like that I work with, was there in his earlier years when they developed it, and it was some pretty cool stuff. I think it was, I don't know, 2020 or something. But in 2019, Ixnos was the first model to do that, actually, like ever, for this to tackle this specific problem. And it was just a simple linear model or network, but it did a pretty awesome job. And so, going back to what I was saying, we have the known values in known sequences, and all we need to do, right? So the job is basically just creating a model to predict it on, or take that. That's our training data, and we just compare it, and then we update our values in the model to make better predictions. And hopefully on unknown data, we are pretty damn accurate. I don't know, but that's it. Sounds really, really dumb. Maybe if it's coming from me, but that's the context. Now, part 2, right? The next question. So how do we actually encode this, right? Because at the end of the day, when we work with models, tensors, right, it's all numbers, right? So how do we actually encode sequences like this? The unfortunate thing in, I guess, computer science is that you don't know, or at least in AI, you can't, models don't know anything about position. And what I mean by that is, given a sequence or index based on a certain, I know LLMs are popular these days, but so we'll call these little guys tokens, right, in the sequence. You don't know anything about the position. There's no number that can just represent, a single number that can just represent a position. And you would probably thinking okay, maybe if we have an array, right? So it's 0, 1, 2, 3, 4, right? 0-based indexing. Oh, why don't you just feed the model 3, right? It's not that easy, because you're supposed. Now, I'm not an expert at this, right? So don't take my word for it, but you just can't do that. One, when you think about scaling, right, you have to kind of normalize values. That's one example I can think of, but you can't just feed in the index and learn off that, right? So now the question is, what's the solution to this? Well, for Ixnos, there's also another paper that tackled this problem, and it was made in 2024. It's called Translatomer. You can do so there's this thing called one-hot encoding, right? And this isn't just a biology thing, right? This isn't just applied to this context. This is one-hot encoding is actually applied to many things. For example, when softmax, right? If you work with something like the MNIST data set, you have to one-hot encode. So your network would be what? List of 4, 5, 6, 7, 8, 9, 10, right? Your model will have, okay, this is talking about the output layer of a network that is predicting handwritten digits on MNIST, by the way. That's the clarification, because I know I just mumbled some words and they were kind of jumbled up together. Anyways, if you have 10 neurons like this, right, the idea is that the first neuron will represent a prediction of 0, 1, and then the next is 1, the next neuron is 2, the next is 3, 4, 5, 6, 7, 8, 9, okay? So, why do we talk about this? It's because when you're working with tensors, your output is just essentially softmax. So you apply all of this to softmax. And that will give you a vector of the size 10, because that's the same size of your output layer, of new values. And the thing about softmax is you can look into the methods of it in yourself. I'm not going to explain it, but essentially it just gives you a probability distribution over these 10 values, or essentially probabilities that the input data or the image that you just fed it is that number, right? Hold on. There we go. Okay. So, why do I talk about this? Well, how does a model know that this neuron is 1? How does it know, right? you need to do, oh yeah, one last step that I forgot to talk about, because you can technically use zero-based indexing. You need a loss function, right? A loss function compares, you're supposed to compare the distribution, the true distribution between your predicted distribution in this case. And you need to one-hot encode. So I can actually probably switch it up. Maybe it's a better explanation. Coding for softmax. Maybe this article is good. Oh yeah, okay. So something like this, right? Okay, that's a better definition. So why do I talk about the loss function? It's because we have our true probability distribution, which is like the set of floating point numbers, like in an array of size 10, right? But the big but, how do we know our true distribution, right? We can't just take like the number, like let's say the true distribution was, okay, this number is literally a 0% probability that it's going to be 0 to 4, and let's say our true number was 5, and that means 6 to 9 would be a 0% chance. It makes sense, right? Because like in the real world, like if I have an AirPod, like this is my AirPod case, right? What's the probability that this is, I don't know, my mom, right? Like 0, right? Because it's literally impossible. There's no universe that this is my mom, right? I don't know, maybe. Anyways, you can't just use index-based values because probabilities are from 0 to 1, right? This is the 6, so if our true thing is 5, right? Our index is 6, but we can't just use 6 to calculate that, right? Because, again, probabilities are from 0 to 1. So we use one-hot encoding, which is just essentially giving that true distribution will have an encoding of 0, 0, 0, 0, 0, and then at the 6th index, which has 5, that will be 1, and then everything will be 0, 0, 0, 0, 0, right? And so we're working, so our true distribution will be represented, so true will be represented by, hold on. Okay, there we go. FP, right? It's like a floating point number. And then, why is it not working? Okay. Wow, my Wi-Fi is very slow. Hold on. Let me just plug in my thing again. Okay, there we go. Wow, no, it just doesn't want to work with me today. Okay. Is this better? Thank you. Right? So, our true probability distribution is this, and then our predicted, so predict distribution is, I flipped it, didn't I? The predicted is floating points. Hold on. My Canva is so slow today. Wow. Give it a bit. I will wait out a bit. Okay, cool. Hold on, this is so annoying. I'm sorry, guys. Hold on. Okay, sure. I don't know, bro. That's so dumb. Cool. Maybe I can just use my hand. That's not that bad. That is actually not that bad. Okay. And then I'm just gonna erase all this, and then, right? Okay. It'll be 0, 0. Right. Do I just have to be slow? Okay, Canva is just so incredibly slow. Okay, anyways, this, right? So we have our true probability distribution and then our actual predicted probability, like the model's prediction or predicted probability distribution, which is just floating point numbers, right? We feed these into our code or our algorithm to calculate the loss by comparing these two distributions, which is, if you look into it, I won't explain the math, but it's a categorical cross entropy in this specific case for MNIST, right? But then, because of one-hot encoding, right, because we have this 0, 0, 1, 0, 0 thing, then we can actually work with that loss function. Then we can actually do calculations. But before, you can't just use the, sixth index, like how, or we're 5, so the sixth index, right, in the array, right? Because what are you going to do with that? You can't work with that. So that's the power of one-hot encoding. That was a really terrible description, or little lesson, but yeah, so now we know that we can't actually work with the array-based indexing, right? And so what does that mean, right? What does that mean in our case? So we know that we have a sequence. Hold on. Okay, so we know that we have some sequence, so A, C, T, G, A, C, T, G, right? What would the tensor input look like for these types of models? There's multiple ways. There are models like BERT. So there are things like I'm looking at foundational models right now, right? So that's what I'm looking at. And certain foundation models like BERT or DNA BERT use things that are used in NLP for text-based context. So like the transformer architecture, right? What do they all work with? Tokens within sequences, and then they work with those tokens to predict new tokens, right, from a distribution. Like every possible token that can be listed out, there's a probability distribution, and you just pick the highest predicted probable token in a sequence, like to predict the next one. That's for language, right? So some models, they actually just treated ACTG like a string, like this entire sequence as its own string, and they used foundation models that were trained on text sequences and tried to make predictions, biological predictions, on biology sequences. Now, surprisingly, that it seems like it actually worked, right? When you tokenize these sequence of nucleotides, these transcripts, right? it actually does work. And so there's this thing called PCC, or Pearson correlation coefficient, that kind of measures how accurate you are in your predictions, right? So it's not like a direct like comparison between position, like prediction to the actual value, right? There's some weird math that goes on, right? But don't worry about them. What you do need to know is that some models actually treated this like it's a text sequence, right? And they converted that model so that they made predictions, and it worked out. It worked out really well. But fortunately, we lose all the context of biology by doing that, right? So what does that mean? There is a model called Orthros that was trained on mRNA sequences, and what they did, and this isn't a new thing, this was actually something that was done even before, right? But what they did is they have, so you can think of it like multiple tracks or like a matrix. So let's say A represents this, C represents this, T represents this, and G represents this. And what is this, right? This means we have a matrix like this. Let's call it like a box, right? And so let's do this. Bup, bup, bup. Bup, 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 right? So let's look at the sequence. Let's say, actually, I can just erase this, honestly. So how many nucleotides do we have in this, right? We have 8 nucleotides, okay? So this is a matrix, right? Each row will represent an A, and the next row will represent the C, and then the next row will represent the T, and the next row will represent the G. So what does that specifically mean? So let me just draw this. Hold on. And then we have 4 rows, right? So a simple input to this would be a 4 by matrix or slash tensor. All right, and n will represent the length of the sequence, right? So in this case, because in our simple case, we have 8 nucleotides, so we have 8 we have a sequence length of 8. What does this mean? Well, let's say an open box. Hold on. That's so dumb. Why is this not working? Wow. Hold on. Let me check how much. Let me check how much. I have 60% in my Apple Pencil. That's so dumb. Okay. Give me a bit. Okay. What? It's just not working, I guess. Hold on. Okay. So. Wow, this just doesn't want to work today. Okay. Hold on. Let me search this up. Wow. I don't know. Google can't help me out. I can't find resources that will fix this problem immediately. I did run into something like this, but that was like before in the school year. But that was just because like the tip of my Apple Pencil was just broken, so I have new replacements, but this one's completely fine. Like, this pencil's in great shape. Canva's just not responding to me. Well, let me... Okay, so on GoodNotes it works out, but I don't know. That's just unfortunate. Maybe next stream I can just like find a way to link my iPad to my laptop. But I don't know how to do that. I use OBS. So okay, anyways, let's say, oh great, it works now. Okay. Let's say a dark square or a dark like number in the matrix. This will be a 1, right? And then open squares will represent a 0. So what does that mean? That means each like part, right? It's a one hot encoded sequence, right? So let's look at the column by column, right? We have A, right? A will, so this part will be marked as 1 and everything will be marked as 0. All the other the 3 other elements in that single first index, right? It will be marked as 0. Then we go to C, right? C will be 1, right? Because we know it's C, everything else will be 0. Then for the third, so the third index of the sequence, right? We go look at the third index row wise of this matrix. It will be 1, right? And then G will be 1, and then this will be 1. Okay, cool. Right, so this is what our sequence is looking like, and this is how we encode it. Now that we have a matrix, we can actually feed it into a model, and now we can create, like, start making predictions, and that's pretty cool. Now specifically, I talked about Orthrus. Orthrus has another track, so there's 2 more tracks, right? So this input will be 4 tracks. The other 2 tracks represent other things, but I'm not specifically concerned with it because they already did that job for me. My job is the model, using the model itself to generate embeddings. So the progress so far was that we feed something like this. I'm able to feed things like this, so I'm able to take a sequence, and right now I'm using the genome kit library, and my advisor said just use that for now. On other known sequences before we use our lab data, because I'm still sorting that out, but I might work on that today. I don't know yet. But so far I'm able to feed this into something called Orthrus, right? So let's call this Orthrus 6-track. Right? And then that will yield me a 500, so the 6-track Orthrus yields 512 embeddings, right? Now, the next question is, okay, well, if, I'm not sure how to approach this actually, right? And I'm still thinking about it. It's like a design choice, right? But if Orthrus produces a 512 embedding, do I take the entire sequence and produce just one singular embedding to represent that entire sequence, or because I'm making predictions on the codon level, or the nucleotide level actually, right? So it's one prediction per nucleotide for now. Do I generate embeddings for each nucleotide? And so that tensor would either yield, so I'm thinking, do I yield a 1 by 512 embedding, so singular embedding, or do I yield an n, so let's say our sequence length, do I yield an n by 512 set of embeddings, right? And then do I use that set of embeddings? Oh yeah, and for context, right, we're gonna have predictive model head, right? Predictive model embeddings. Sorry, not embeddings. Model head. Right. And then this, right? So just know that Orthrus is supposed to give me some input, and then I use that input to, well, I make up, well, two things, right? I use that input, but I use it by making some model, some head. The architecture, the structure, everything about it, I'm still working on that, and I'm still trying to decide that. And so I've been reading papers to try and make something optimal. But regardless, the output of whatever that model head is, my grad student already explained it, that it should ideally be, so there's going to be 3 predictions, right? So we have our sequence. So let's actually just take advantage from this graph that I drew here, right? Because at the end of the day, this is what our output would visually look like, right? So, hold on. Okay, right. A, C, T, G, A, C, T, G. And by the way, I don't know if this number is actually 1,000. I haven't looked at that myself. I just, because I'm only given like the metrics, right? But maybe I could spend a lot more time looking into that. And so I don't know. Well, no, actually, I do not know. That's what I was explaining. I know I said that there's going to be one, like, we'll call it a distribution like this, right? But my grad student said we actually have, so there's things called cell lines within the genome, right? So for each cell line, it has there's 3 different like tracks, right? That represent, like, that come from the same transcript, or not the transcript, but the same sequence, right? And so because there's 3 different tracks, I'm actually supposed to output 3 different predictions per nucleotide or per codon, depending on whichever base prediction I'm trying to make. So I'll actually have maybe, like, I don't even know. I'll use 3 different colors, right? We'll use red as 1. So maybe I'll have one thing like that, and then for the last color, we'll make it green. And then maybe I could have, right? So the model is essentially trying to predict over the entire transcript, or the entire sequence, make 3 different predictions. And so what would that mean for me? That would mean the model would have to have a tensor with the dimensions of the sequence length, or yes, because I'm not just going based off the head, right? I'm given embeddings, and the embeddings have a fixed size, right? The head is supposed to have, its output is supposed to be the same length of the entire sequence, because at the end of the day, what was the original goal from 2 streams ago? We want to try and feed the entire sequence, or as much of the sequence as possible, right? So it would be, if the original sequence length is n, our output tensor would be, oh, hold on. Bang. Okay. Our output tensor would be n by, okay, it would be n by 3. It would be n by 3. Hold on. Yes, it would be n by 3, because for each nucleotide, we have 3 predictions, right? So if we have n nucleotides, we'd have n times 3 predictions. We use those values to calculate our loss. And so now that we know we're trying to output an n by 3 tensor, we'll feed that into our loss function. So loss, and that is what we're doing today. That is the goal for today, right? Right now, what my model looks like, it's just a very simple head. So currently, right, if I generate embeddings, or actually, hold on. Okay, I'm in a compute node right now. So let me just write a Python script really quick, or not, execute the Python script that I have. ls clear So, okay, I'm in my, wait, let me just double check. Okay, so I'm in my riborthris directory. So, if I execute Python, so scripts slash generate embeddings.py, right? Because that's the script that I have right now. Let me see if you can, okay, yeah, so you guys can't see this, okay? I'll use the restroom really quick, but when I am back, then hopefully the output is this. Okay. So, Okay, cool. So my script's finished running, and so here you can see that we have a sample script. So this is from the genome kit. This is from a random cell line, which would be, oh, right here, the BCL21 or 2L1, and I think it should be 12 at the end. But this cell line right here, alright, so this is a cell line, and the cell line has a sequence, right? And that, in this, whatever data format you use, there's different information that is also, what's the word? Affiliated with that sequence. So here, I took a this is, by the way, this is a very, very, very small sequence compared to what the entire thing is. Like, this is of small length, right? But as we can see, right, we have, like, so imagine we take this entire sequence, I fed it to Orthrus, and right now its output shape, right, is, wait, okay, oh no, so the input to Orthrus, right, so we see that it's one transcript, 6 tracks, right, so 4 of those tracks represent ACTG, and then 2 other tracks with other biology context, but we're not really too, not familiar, but we're not too involved with that part. And then there's 2,578 nucleotides in this subsequence, or this sample transcript, right? And so we feed 2,578 of those nucleotides into Orthrus, and then right now I have it where, so one transcript, we have for each nucleotide, so of each of the 2,578 nucleotides, we have an embedding of 512 in length. And so that was the current approach that I have right now, where it's n by 512. But I will have to ask my advisor to see which is better. My guess is that if we can just go based off one embedding to make a bunch of predictions, that is a lot more, that's a lot easier, and it's a lot less expensive in terms of compute, right? It's literally n times more faster, right? And so, but the reason why I came for this latter approach is because I just don't think a single embedding would provide enough context of our entire transcript. I just find it so hard to believe that that approach would give us meaningful results, right? Sure, it's faster, but at the end of the day, what do we want? We want results. But if I'm making predictions at the codon or nucleotide level, then if I have an embedding that represents learned information from each of those codons or those nucleotides, that might tell us something. Then that might lead to something pretty cool, pretty awesome. And so right now I have it set to this approach, but we'll see. We'll see what happens from the next meeting, which is 2 days from now. Anyways, so that's our output from Orthrus, and then that will turn into my input from my predictive model head. And because we have this one extra dimension, I just call in torch.squeeze. So we have this tensor, right? Let's say it's A. We just use the squeeze function, and all that does is literally just take out one dimension, right? It literally squeezes that tensor into a smaller tensor by one dimension, right? Because we don't care about, oh yeah, we have one transcript. We know we have one transcript. Then after we squeeze it, so yeah, here, right here. So currently, my my model looks something like this. So we have 512 neurons, right? Can you guys see this? Yes, you guys can. Okay, cool. So this is of length 512, okay? And then we need an output shape, right? Because like I said before, we need an output shape of n by 3, right? So our head would look something like, hold on. Okay, yeah, so this is where I went wrong. Initially, when I wrote the script, I thought the cell lines included information. Each cell line was its own prediction, right? And so I thought, okay, given my data, right, how many cell lines there are, I'm making that many number predictions. Wrong, right? Now I know there's only 3. So this actually needs to be, this needs to be 3, right? But right now I have it set to 25, right? But each neuron should be a prediction, I believe. And so then we can take, so each head, so we need 3 different heads. Oh wait, hold on. Maybe, okay, no, I lied. That's so dumb. Okay, this needs to be ideally of a length n, right? So each head, its output tensor needs to be of length n, right? And so then we'll have like, hold on. Hold on. Okay, cool. So one head would look like this. Okay? And each neuron will have its own prediction. And so then that means we need 3 heads. So then if we feed it to multiple heads, our final, right, so let's say this is one predictive head. Okay, cool. So, alright, my Canva is very slow. Okay. Well, while I wait for this to load, the idea is that we have one head, and then so that would because we have 3, the output from the entire pipeline should be 3 by n, and now that makes n by 3. I can transpose it; it doesn't really matter. But yes, that should work. And now we have our pipeline. That's our pipeline. But right now, the model itself, right, the head, is just some simple linear model, and that itself is already a lot of parameters, right? Because if we have n by 512 by 3, yeah, so we have 3 times 512 times n weights plus 3 times n, so hold on. I don't know what the number of, so the number of parameters, right? Wait. I hate slow devices, bro. This is so annoying. So cooked. or maybe my Wi-Fi is just slow. No? Hold on. Let me try and reload Canva. Nothing's deleted, right? Okay. No, this should be fine. Okay, cool. So our number of parameters, so the 3 heads. Right? So for each head, so we have, okay, so let's say we have 3, so 3 heads times, right? Now we just need to calculate how many parameters are in each head. And so we know that for each head, right, it would be n times 512 weights, right? And this is just assuming I only use one layer, right? So for one simple, right, we're going to denote this in big emphasis that this is a simple MLP. Cool, cool, okay. So for each head, we have n times 512 weights. Correct. So it would be 512 embed elements, right, times n weights, or not n weights, sorry, n nucleotides, right? So those are our weights, right? Actually, yeah, we'll just note that as weights. Weights plus plus, okay, it should be n biases, yeah, n biases, right? Does that sound right? That is right, that is correct. Cool. Okay, so in total we have 300 times, and then in parentheses 512. So this should be the number per 512 times n plus n. Yeah, this sounds perfectly fine. And so essentially, wait, I wonder if I can simplify this actually. Could that just be 513n? Yeah. Yeah. So we'll have 513n parameters. So which is just what, 3 times 513? That's just 1539 times n. So 1539 times n. Wait, so this could just be simplified to to 5,000, 15,000, right? 15,000 39 parameters. Okay, cool. So let's test this theory out, right? Let me just change. Okay, hold on. I know I've been kind of yapping a lot, but I want to try and test this out and see if the calculation is right. Hold on. Okay. Cool. So I need to make sure that this is 2,578. Okay, well, assuming that I only have one head, right? Because this is a script for just one head. So I'll just divide it by 3. So we'll go with 513. We'll go with 513 by n parameters, right? I think it should be, and I am not a mathematician, so let me search that up. Desmos Scientific. Okay, 513 times 2,578. Yes. Okay, so we are trying to train a model that has 1,322,514. So that's just one head, right? And then if we just take that answer, so ans is it, how do you 3 times answer. Okay, let me test that out. So let me go to my old script. Okay, I'm in Vim right now, so I've been also trying to learn Vim. Oh my god, I'm out of it. Cool. Okay, let me just SSH really quick. Cool. Okay, nice. I don't need to be in a compute node. Yeah, I'm just editing text. Okay, cdw cd report this clear. Okay. Cool. All right. Now that I'm in Vim, I'm going to edit this really quick. So, first we need. Okay, that's the end of the line. Okay, where do I hardcode 25 in here? No. Wait, no, that's not my. Okay, there we go. Yes, I do. Here, we're just gonna call this. I need to be in insert mode. Okay, we will just create a variable and let's call it prediction tracks, right? Okay, num prediction tracks, and we are setting that to 3, correct? Because num prediction tracks. Oh my god, it's slow again. This is so tragic. Okay, cool. And I just like to stay organized. And we know that the embedding shape is 512, right? And it will always be 512 because of Orthros. Cool. And then I wonder, let me search up PyTorch function to count number of parameters. Okay. What is p.numl? p.numl. Oh, okay. So, and then model parameters. Let me double check. What is that? Or can I just go? Let me just go to the PyTorch documentation. Parameters. Okay, cool. Okay, so let's just say, so now we have a 512 input layer, and then n. No. This is wrong. This needs to be sequence length. Sequence length. There we go. Right. Sequence length. And then hidden. Hidden is our hidden input, right? We will do hidden dot shape. Can we do hidden dot shape dot 1? Does that work? Does that work? Hopefully that works, no? And it should be the 0. Yeah, that should work, right? Because this should give us 2,578. Yes. Okay. And then so we have our architecture over here. And then so let's just say our total parameters, right? Let's just say that's equal to, so it would be a tensor or an array. So we could do sum, and what happens in that sum? I found the null function, which was recommended. Okay. Can I do... Wait, no. That doesn't look right. Hold on. And then that looks right, because so for each parameter in the model parameters, we'll sum them together. And our model isn't called model, it's called head. And we're going to print yeah, it's just so slow today. And we're going to print total params. Okay, does this look right? So Okay, so our sequence length, right? Head is equal to torch.nn.linear 512 by sequence length. Cool. And then for each parameter in our head parameters, we're nummelling them. Let me double check this. Okay, this looks right. Yeah. Okay, cool. I'm gonna escape, and then okay, let me test this out. Clear ls. So for one head, what did I say it was gonna be, right? What did I say it was gonna be? 1,322,514 parameters? Yes. So we're going to test that out. Python scripts. Alright, let's see. Uh-oh. What's wrong with this? Oh, am I not calling it? Uh-oh. Oopsies. Wait, what the fuck? Wait, can I not shift? Oh my goodness, I can't. Oh my god. Wow, hold on. Okay. This is just a Vim thing. Oops. Can I not shift in Vim? Oh my god, I'm so dumb. I'm not in insert mode. Oops. Alright, there we go. Okay. Boom. And then we can call it. And then I'm going to escape. Then I'm going to write back. And then I'm going to quit. And then I will... Hopefully that works. Okay. Let's see. Oh yeah, there we go. Okay, see, now that's exactly, yup, that's right. Okay, so, we are correct. We are correct. That makes me pretty happy, actually. So, Here, yeah, we are correct. As you can see, so that's what our current head looks like. We know that our sequence length is 2578 for this script, right? But it's just going to be n, right? So we know that for a fact, that this equation is correct. And so we will have, and since our case we're having 3 predictions, right? We have 1539, right? Because 512, and then we only have 1 layer. So yes, this is all dependent on our sequence length, which is pretty cool. It's pretty cool. Okay. Cool. Okay, anyways, going back, right? So that's what our head looks like, and we know for a fact that's what our code is doing. Today, we are going to be taking a look at the loss function, which my grad student described it as a multinomial loss function, since it's not going to be directly MSE. Some models, like Ixnos, it uses MSE, right? And if, let me just double check. Okay, cool, hold on. Okay. There we go. So, the Ixnos paper, which is just a simple linear model, right? So they didn't have embeddings, didn't have any of that, right? It's just a simple linear model to predict ribosome occupancy, kinda. So a series, blah blah blah. Importance of each composition predicted performance was computed as the difference in MSE between the reduced and the full models. Cool. Okay. So, yeah. But I have the script, and so we will take a look at that. But that's the current loss. So, our loss function, let me double check. I need to charge my phone. Okay. Cool. Let me. Okay, so the loss function, let me take a look at it. Oh, I need to reset my compute node, right? Shoot. In a bit. I'll reset it in a bit. Okay. I need to think. Okay, so I need to go through. Actually, let me just reset the node really quick. Exit. Clear. IDEV. 100.dev t with an allocated time of 2 hours. Whoa. What? Oh, am I missing a flag? Yeah, I am. Okay. Okay, neat. I'm in a compute node, right? Alright. Okay. So, where am I? Touch. So we're gonna create a new file called loss.py. Right, so, and if you look into the... Nice! Nice. So vim... oh wait, I also need to... conda... Let me just make sure conda's on. Okay. Activate... Uh-oh. Source... Wait, hold on. Okay. Source... mini conda 3... TC... switch. Okay. Conda list. Okay. So, C scripts. Cool. So vim. All right, now we're gonna vim into our loss.py. So, let's try printing really. Oh, oops! I need to be in insert mode. Print. Hello world. Right? Classic. and we're gonna save that. Oh, oops. Escape, and then now we're gonna try that. So Python loss.py. Alright, nice. Print hello world. Cool. Now let's actually write the loss. So okay, dim. So first we need to, okay, this is weird. I need to go in insert mode first. Nice. So we need to import some libraries. So import torch, and then Orthros already has torch. So from that torch, right, we can import tensor library, right? Now we can do okay, so def. So first function is safe mask mean, right? Okay, and so x, right? Hold on. Oh yeah, I need another library. Typing float. Hold on. My dad's calling. Dad, don't jump. quickly. I do have to go, but this is unfortunately a really short stream. But yes, I will see you guys tomorrow morning. Maybe not morning, but lunchtime.